members. Today I'm going to give my proposal talk on my PhD thesis titled Towards More Accessible Human AI Interactions in Sequential Decision-Making Tasks. Okay. So we're seeing that recently AI is being used to solve increasingly complex tasks, be it self-driving car, delivery robots, surveillance, etc. And there is an ongoing interest in adopting these AI agents into our day-to-day lives. Now, for this integration into our lives to be successful, these agents not only need to be very competent in the tasks they do, but they also need to have certain broader capabilities. For example, these agents must be explainable and advisable. What I mean here is that if the user is confused about the agent's behavior, they must be able to give an explanation for that behavior. And if the user wants to express some preferences to the agent, first of all, there should be means to do that, and then the agent should align with their preferences. Based on that, our objective in this proposal is to enhance the explainability and advisability of AI agents by essentially focusing on refining the human-AI interaction process. And our focus is on agents that are solving a sequential decision-making task. That is, the agents must compute a sequence of actions to achieve the goal or complete the task. Now, what's really challenging in these human-AI interaction scenarios? So the biggest challenge here is most of these modern AI systems use deep learning-based representations, and based on that, they complete the task. So they make the decisions. But typically, these representations are inscrutable or incomprehensible to the users. For example, let's take this model-based reinforcement learning agent. What this is doing is, it is taking the state, it is using some deep net to encode the state into some encoding, and then learning some transition dynamics over it, which then it further uses to take its decision. The problem here is that this state encoding and the features it has made are completely uninterpretable to the user, and hence we cannot use those as a means of communication between human and the agent. Consequently, in AI literature, mostly this has been solved by looking at the only common medium between the human and the AI agent, and those would be images, which sounds reasonable, but there are issues with it. The issue here is, let's say explainable AI that often employs saliency maps as explanation. Now, this is great for one-shot decision-making tasks like classification tasks. However, this will not translate well for sequential decision-making tasks where we would actually have videos of agent behavior. Let's say somehow you took snapshots of the agent, snapshot of the agent's behavior and showed some saliency over it. Great. But even then, the explanation is tied to the environment dynamics, and just by looking at an image, the user cannot be sure what part of dynamics you are referring to. So these are kind of infeasible for explanations. On the other side, you have advisable AI agents that use trajectory rankings, like reinforcement learning to human feedback. Here, you basically show trajectories to the user, they'll rank the trajectories, and you will learn a preference function over it. Great. However, this is a very weak signal for preference, so you would typically require a lot of feedback from the user. Consequently, these are impractical for everyday scenarios. Okay, so in this proposal, what we are advocating is that the human and the AI agent should communicate the way we humans do, that is over language. More specifically, over some symbolic representation, which makes sense to both the human and the agent. Consequently, they're saying that there should be a symbolic interface between the agent and the human, which consists of some shared vocabulary, and the communication should happen using this vocabulary. Now, another challenge which is often overlooked in human-AI interaction is personalized interactions. Now, each user is potentially different with some unique background knowledge, expertise, and preferences. The communication system must be versatile enough that any kind of preferences could be specified to the agent. Finally, the explanations themselves should match with the user's level of expertise in the task. With that being said, in this proposal, we are giving this framework for explainable and advisable AI. What's common in this framework is that we have a symbolic interface, whereas the agent's own representation of the task is inscrutable. And we have particularly three components in this interface, which I'll talk about one by one in this talk. The first component is the explanation generation part. Particularly, this will generate symbolic explanation for the user. In the second component, we put additional constraints on the symbolic interface, and that way the agent is able to personalize the explanation for the user based on their background knowledge of the task. And the third and final component allows users to add new vocabulary terms to the interface, thereby giving unique preferences to the agent. So I'll start by showing how our agent can generate symbolic explanations for the user. So here's a concrete example where we have an agent that is trying to solve the task of Montezuma revenge. This is an Atari game where the agent's goal is to get to this key. Now here, the agent is solving this task based on some RAM state representation of the game. So that encoding would be inscrutable to the user. Instead, we have this shared vocabulary which contains things like agent in air, left door close, etc. These are basically propositional variables which are either true or false in a state, and these are grounded as basically binary classifiers. So in this component, we are trying to deal with answering contrastive queries from the user, which ask questions like, hey, why X and why not Y? Where X is the original plan and Y is the alternative plan or foil. Now, how to answer these kinds of questions? So one, the agent can say, hey, the foil has an invalid action. It is a kind of action which is either inexecutable in the state or it violates some hard safety constraint of the domain. Or the agent can prove the foil is costlier than the original plan. So as you can see, both of these things are tied to the environment dynamics. Hence, what we do in this component is learn a symbolic model of the underlying dynamics of the agent, of the task. So this symbolic model consists of set of propositional variables. These comes from the vocabulary, and more importantly, there are two sets. One is a set of actions which are described with preconditions. Preconditions are basically concepts that must be true in a state for that action to be executed. The second thing is you need a cost function. This cost function gives the cost of executing action in presence of some concepts. So based on this, we can actually produce these explanations, as I'll show in this example. So let's say the user comes up, the agent says, okay, this is what I'll do. I'll go to the lowest platform, I'll jump over the skull and I'll get the key. The user says, why don't you go through the skull? Take the move left action here. So in this case, the agent, looking at the environment dynamics, basically learning these components, can say that, hey, move left will fail here because the precondition skull not on the left is missing from the state. Similarly, if the user says, why don't you attack the skull and just get rid of it? The agent can say, the attack action costs at least 500 when skull on left is true, thereby making the foil cost greater than the original plan cost. All right. So if you may notice that we do not need to learn the entire environment dynamic model. Rather, all we need are some preconditions of actions or this cost function abstraction. So in this proposal, basically, we do sampling in the environment to learn these kinds of model components. And I'm going to go over how we learn the precondition, but how we learn the cost function is detailed in the document itself. So we have this foil. How to learn the precondition? For this, we have this foil that the user suggested. And obviously, this has an invalid action that was taken in this state S failed. So what we do is, we basically see all the concepts that are missing from this state because one of these is the missing precondition. So this is our hypothesis set for the possible preconditions. Then we basically sample states around the original plan and the foil. These are the sample states. We look at what are the concepts that are present in this. The precondition would be one of them. These are all the states where actions is executable. So one of these concepts would be the precondition. And we simply take the intersection of these two sets because the precondition would be present in both the sets. So we essentially keep on doing this for some large number of large budget, sampling budget. So eventually only the precondition concepts would remain in the set. So we can give that as an explanation that that is what was missing in the original state. Okay. Having said that, what we also need is, it is actually important that the user knows how much it can trust this given explanation, so that they can basically calibrate their trust. So to do that, we basically compute a confidence in the generated explanation, like what is the likelihood of the explanation being correct. To do this, we basically have define a probabilistic model that computes the confidence in the explanation, and it considers two things: correlation between concepts, which I'll explain shortly, and noise in the concept classifier, which is obvious because classifiers cannot be completely accurate. Okay, given that, this is one of the probabilistic models we use, which is basically saying, hey, if a concept C is present in state S, there can be two unique causes for it. One, which is favorable to us, that action A is executable in S, and the concept C is a precondition of A. That is why it was present here. But there is another way it could be present, and that could be that just other concepts are there in state S and they are correlated with this concept. Okay, given that, we can basically compute confidence, and more detailed formulas are in the proposal. But here is a simpler case when we assume that we have a perfect classifier. So now when we sample a state S, we find that A is executable and the concept C is present. What is the probability that it is actually a precondition of A? So instead, here I'm computing what is the probability that it is not a precondition of A, and that is directly proportional to the concept C being present in that state given the other components being in that state. So this is the correlation. So basically what intuitively what this is saying is that if you usually notice this concept with all these other concepts in the state, then it's not a strong evidence, and thereby the possibility that it is not a precondition would still be high. So you would have to sample a lot more states where you keep encountering this concept before you are confident that yes, this is a precondition. So based on these formulas, we modify our explanation generation procedure, and it will now only output most likely explanations to the user. So I'll go over the evaluation quickly. We basically evaluated our techniques on two domains: the Montezuma revenge domain and the Sokoban domain. Sokoban domain is again a game-like domain where the task is to push this box to this target. We had a total of 7 foils, where 5 were invalid foil, 2 were suboptimal foils, and in all cases we did identify the correct explanations. Now, the other thing is that as the sampling budget increases, our confidence in the explanation increased as well, which makes sense by the formulas. Other than that, we also conducted 2 user studies. So in user study, we wanted to see how useful are basically our symbolic explanations. So in the first user study, we basically wanted to see if people prefer explanation that establish these model components over explanations with just simple foil information. So simple explanation are that we just mark the action that would fail, or we basically look at the per step cost and just tell the user what is the per step cost. We don't specify any concepts that are related to whatever these two things are. And we did a within subject study where people were shown a foil along with both these kinds of explanations. So we saw that people do prefer symbolic explanations. In 19 out of 20 cases, they did prefer symbolic explanations, and the results were statistically significant. The second user study that we did, wanted to see if concept-based explanation provide a better task understanding than saliency map-based explanation. So this is again more of a basic premise of our proposal anyways. Explanations. In this, participant played the Sokoban game and they were given explanation whenever they took an invalid move. So it was a between subject design where participants were given either concept based explanation or saliency map based explanation. And we saw that when given concept based explanation, they could really get the environment dynamics quickly, and the average time taken and the average number of steps were lower than the saliency map based explanation. Okay. So far we have talked about how our framework can generate symbolic explanations. So now I'm going to talk about how the agent can personalize the explanation based on the type of user it is interacting. Okay. Before I go into that, I want to just point out that the explanations that we are looking at are basically model reconciliation explanations as given by Chakravarti et al. So these explanations come into play in scenarios where the robot's model of the task is different from what the human's expected model of the robot is, which for brevity I'm just going to call human's model of the task. So a plan that is optimal in the robot's model may be suboptimal in the human's model, right? In this case, the robot must basically correct the human model and give some model updates to make sure that its behavior appears explicable to them. They can justify that behavior. Let's take a simpler example here. The agent goes from here to this green circle, going over some puddle. The human mistakenly thinks that going over the puddle can damage the robot. So there is some cost in his model for this action. So the robot must give an explanation saying, hey, going over the puddle incurs no cost. So here we are updating the human's model. There's a model update. So these are the kinds of explanations we are interested in this work. And the symbolic explanations discussed in the previous component were also model updates where we were in a way updating the precondition in the human's model for actions. Having said that, in this work, we are claiming that each user can have a different model of the task. That is, they may require explanations that are tailored to their model of the task. And we make a simplifying premise here that let's say there are multiple types of users, such that users of same type will have similar model of the task. Users of different type can have different models. So explanation should now be personalized based on users' type. So here's again a concrete example. We've got an agent. This agent is a disaster rescue scenario where the agent's task is to pick up this victim and move them to a shelter location. And there are many actions that can do along the way, one of which is to pick up this first aid kit. So there are two types of users here. This is a simplified example where user of type A believes that picking up this first aid kit is unnecessary, and user of type B believes that going over the puddle can damage the robot. So what are the challenges when we assume there are types of users? So the first challenge is that we do not know what are these different types of users, and we do not know their model of the task, which is required for generating explanations. This is solved during the training stage of our framework, of our solution. The second is that when generating explanations for the plan, the user's type, the type of the target user, the current user is also unknown. And the final challenge is that when I'm generating an explanation, there is a communication cost involved. So the agent must balance the communication cost and the cost of showing incomprehensible behavior. So all these challenges are solved during the interaction stage. Okay. So before I go into the training stage and interaction stage, I want to talk about how we can approximate the model of a given user type. So here we follow the model approximation presented in Sarah et al., where we assume that we have access to a set of explanatory messages E, where each message corresponds to some symbolic information about the model parameter. So in our disaster rescue example, running example, we would have a message which says, hey, the reward for going into the state with puddle is 0, and it's not a negative reward. There is no cost associated with it. Thereby, we can approximate the user's model of the task by learning what we call as a labeling model. The labeling model is simple, and you can, if given the data, you can use machine learning techniques to learn this. Essentially, it is a function which maps state, action, next state, or a transition, and a set of messages to 0 or 1, where 1 means that the user of this type, which has this labeling model, will find this transition to be explicable. 0 means they'll find this transition to be inexplicable. So given this labeling model, we can enumerate over all possible explanations and then explain any kind of transition to that particular user. Okay, this was just a preliminary, but note here that given this set E, our explanation techniques would be agnostic to the task representation used by agent, thereby compatible to work with agents with inscrutable task representations. All right, now coming to the training stage. Here, our objective, remember, is to learn the model of each type of user that can be, that the agent can possibly interact with. So for this, we collect training data from a set of observers. The data is of this type. You have transition, you have a message, and you have an explicability label given by the observer. Now, what we essentially do is cluster this data directly into user types. But so the detailed procedure is in the proposal. But the core trick that we use here is that we project each observer as a vector theta naught, where theta naught represents an estimate of a set of messages, which when given to the observer will make any transition appear explicable to them. We cannot calculate this exactly, but with the data, we can get an estimate of it. And so in this particular embedding, observers from same type would be clustered together because they would need similar explanation. Thereby, we will perform clustering in this embedding. So once we do that, we would have clustered observers into their respective user types. After that, we can basically retrieve whatever data was collected from each of the observer, and then we can learn the labeling model for each of the user types. So at this point, we additionally learn a confidence measure for each labeling model, which will give the probability of the label given transition in the message. Where recall, the label is just whether the user will find this transition to be explicable or not. Okay, given that, we can now move on to the interaction stage, where we would have a user, we would have a plan, and we want to explain that plan to the current user whose type is unknown. All right. So interaction actually happens in steps, where at each step, a part of the plan, a prefix of a plan is shown to the user, along with some explanation. And the user is supposed to look at the explanation and then mark each of these transitions as either they found it to be explicable or they found it to be inexplicable. So notice here that when they give us that information, that is our evidence to what their type is. And that is what we leverage in that is what we use to infer their type. Another thing is that the total cost of this interaction would be a linear combination of the communication cost and inexplicability cost. All right. Having said that, we want to basically reason about the hidden user's type and optimize for the cost of interaction. So we can compile this problem as a partially observable Markov decision process. In this POMDP, the user's type becomes the unobservable variable. The reward function will capture the cost of interaction, and the actions that the agent can take are explanatory messages. With that, essentially what will happen is that the POMDP will give us a policy over belief state, where this is the belief state. The belief state is basically our predicted probability distribution or inferred probability distribution of the current of the possible user type for the current user type. So here we are saying that there is a 60% chance that the current user type is of type 2. So POMDP gives us a policy from this to what explanation should the agent give. So all we now need to do is to update this probability distribution as we interact with the user. So the belief over type T is basically proportional to the likelihood of that type T giving us the observed variable, which we get from base rule. Okay, so why we use POMDP? Here's why we used it, because POMDP can actually take information gathering actions that can reduce the uncertainty in user types and then basically generate explanations for that particular type down the line. With these techniques, basically, okay, so the problem with POMDP is that usually they are like computationally very expensive. So we had to use approximate POMDP solvers. Particularly, we used QMDP and POMCP solvers by Littman and Silver et al. We adapted them for our problem, and we made our own solver, the QHR solver, which was an approximation of the QMDP solver, which computed suboptimal explanations, but the computation was very fast. With that, here's our the evaluation. I know there are a lot of numbers, but I'll get to it. So there were 2 domains, and where we evaluated, and across 4 scenarios. One was the disaster rescue domain, where we specified the 5 user types and what their model would be. Then another was a 4 rooms domain. This is a standard MDP domain, where the 3 scenarios, where we varied the number of user types between 2, 3, and 4, and their model parameters were randomly selected as opposed to us setting the model of the user types. And for all our experiments, at least for the computational one, we used simulated users. And we also defined a baseline solver, which basically treats every user as if it belongs to the same user type. Almost done. Finally, we have this, in our experiment, we varied the communication and inexplicability trade-off parameter, lambda. And for each value of lambda, we generated 3 plans, and we computed the cost of interaction for explaining these plans to each of the user types that have been defined. Finally, we had the evaluation metric, which was a regret metric, which takes the difference between the solver cost, this is our solver, and an oracle cost. The cost of this is the cost of interaction for an oracle which already knows the user's type. So here's are the results. Basically, you can interpret lambda as the cost of one explanation message given to the user. So given that, we have these different costs for Oracle agent, and we can see that both QMDP and POMCP approaches do not produce any, this is the regret, so this is the additional cost for these. So we can see that all of these techniques do not produce too many extraneous explanations, and thereby they are personalizing the explanation for the current user as compared to the baseline. So we also did a user study. We wanted to see how useful is actually personalizing explanation as opposed to just giving as much information as possible so that they can find the plan to be explicable. So we did the study over the disaster rescue domain. It was a between subject study where there were 2 kinds of explanation. One was personalized, obtained by our solver. The other was conformant explanation, where the explanations were generated such that they would make the plan explicable to any type of user. So we don't care what type it is, we'll generate explanation. It will be explicable to any user. So this was compared, So it was a between subject study where we compared the interaction between when using this or this across 3 objective measures. One was the total interaction time. One was the total number of inexplicable transitions at the end of the interaction. And one was a quiz score, where we basically quizzed the user and asked them if they remembered the updated model parameters. Given that, we found that personalized explanations were outperformed conformant explanations, and the values were statistically significant. Okay.
Can I ask a question while you're taking a drink? What is
That's the best way to ask.
you can finish drinking.
Yeah.
What do you how did you compute your p-values on that previous slide? What's the test you ran?
Two-tailed t-test.
What,
Two-tailed,
Okay.
two-tailed t-test. Okay, so now we have seen how to generate symbolic explanations, how to personalize explanations, and now I want to talk about our final component. This is a work in progress where we want the user to be able to add new vocabulary terms to this symbolic interface. So again, let's start with a concrete example. This will be our running example. So we have here a Minecraft domain. Here the agent's task is to create a ladder and put it at the target. There are two ways to do it. One, it can pick up planks from here, craft the ladder, and then put it at the target. Or it can go in this storage area, denoted as this green box, pick up the broken ladder, craft, repair it, and then put it at the target. Given this Minecraft task, and the state encoding we use here is inscrutable to the user. Now, again, we have a symbolic interface between the user and the agent. This has some terms already in it. Now, the user wants to specify a preference where it says, hey, avoid states where in storage area is true, because the user has a preference that the agent does not go in the storage area. It should actually use this part. So, but this concept in storage area is missing from the symbolic interface. That's our problem setting. So our objective is to learn these concept rounding on the fly while minimizing the feedback that is required by the user. So this project is all about learning such concepts online. So, what is the actual problem here? So basically, to learn the concept classifiers, what we need is positive and negative examples of the concept from the user. Now, what we could potentially do is basically from the state space, randomly select states, query them for the user, and ask them for their label. But the premise or the scenario we are specifically looking at in this component is where the positive examples, these are these green patches, are very rare in the state space. So if you went with random sampling, you would require a lot of samples before enough positive examples have been collected to train your classifier. So this could be very inefficient. Instead, what we are advocating is that we should gather likely positive and negative examples of the concepts using some heuristics, and then query the user for their actual label. So based on that, here are the three assumptions we make to gather likely positive and negative examples of concepts. But we always check the actual label from the user, so we're not always just estimating the labels. Okay, given that, the first assumption is that we have a causal relationship between concepts, where particularly we have a causal relationship between a concept that is our target that we want to learn and some concept that is already in our vocabulary. So causal relationship is basically a directed graph where each edge, Cx to Cy, represents a precedence relation, which is basically saying that you need Cx to be true in the current state if you want Cy to be true in the next state. It is required for Cy. So what this here means that is the agent must be in storage area so that it can have the broken ladder in the next state. And here it is saying that it must have the broken ladder so that it can get the ladder in the next state. Okay, so this is one assumption. Other is we are assuming concept proximity and rarity, which is basically saying that if a concept is true in a state, then it is likely true in some local neighborhood around that state. And finally, the whole premise that the positive examples are rare in the state space. The final assumption we make is concept region locality. Here we are saying that if we are given a positive example of a concept, then there must exist a localized region in the image which is indicating the presence of that concept. That is, for example, you have in this state, in storage area is true, and this red bounding box is indicating that the agent is in the storage area. Okay, with these assumptions, we basically have a solution approach where we can learn any classifier for a concept CT. But this approach has two components. So I'll first go over the two components, and then I can give the exact approach, basically a high level view of it. So let's talk about the components. So given a causal relation CT to CK, there are two ways to get labeled data for CT. So these are the two ways, but the common step in both these ways is that we'll first collect some seed examples of CT using CK, where CK is the known concept, and this is the precedence relation that has been given. So given this precedence relation, what we simply do is we get trajectories that end in CK. So we know from the precedence relation that the second last state in this trajectory would be a positive example of CT. So the concepts collected this way, we call them as seed examples. Once we have that, we have these two distinct ways of basically expanding our data set for CT. In one, we collect exact labels using informed queries. Here, what we do is we basically do random walk around seed examples. So by concept locality, these are likely positive examples, so we query them to the user. Then we collect negative examples using randomly sampled states because negative examples are abundant. And then we train the classified CT on the collected data. So the classifier trained using this way is what we call as C star X classifier, and we call this like C star style of classification. Notice here that there is more feedback here, but since these are exact labels, we can expect the noise to be low in C star X classifier. The other way to collect data for CT is to basically abuse concept region locality, where we essentially ask patch queries to the user. We ask the user to annotate the patch that is indicating the presence of that concept. So once we have that, we can do template matching, where we can assign any state with a similar patch as positive and state with no matching patches as being negative. And we can train the classifier on this estimated labeled data. So we call this classifier as C hat X classifier, where the concept is CX. Notice here that the feedback required, the feedback required would actually be low, but these could be noisy labels, and hence it could be a noisier classifier. Given that, here is our adaptive supervised learning approach for learning a concept classifier for CT. We have a causal relation CT to CK. We have these intermediate concepts between them which are not known. So based on our previous discussion, we can say that if we know the C1, we can use it to learn CT. But since we don't know that, we need to learn all these intermediate concepts. Now notice that we only need these intermediate concepts to be accurate enough that they gave us some seed examples of the predecessor concepts. So we basically leverage this property here in our work, where for each intermediate concept, we'll start by learning. So the intermediate concept is CI. So we'll start by learning CI hat, which is low feedback classifier. And we'll see online if this is able to get us some seed examples of the predecessor concept. If it fails to do that, then online we'll adapt, and then we'll first learn CI star, use that to get the predecessor example of the seed examples of the predecessor concept, and we can move on. So once this is done, we'll have seed examples of CT, and we can train CT star. So this is the technique in the current state of the work, and we did some preliminary computational experiments on this technique. The evaluation was done on the Minecraft domain, where the target concept was in storage area. There were 3 scenarios, one with 0, one with 1, and one with 2 intermediate concepts between the target concept and the known concept. And to learn the preferred policy, we basically modified the underlying task to give negative rewards when the agent was predicted to be in the storage area. We used simulated users for queries, and for the evaluation metric, we ran the trained agent for 10 episodes and calculated the instances where the agent adhered to the preferred policy. That is, it achieved the goal without going into the storage area. So these are the results. For the results, we evaluated on 2 approaches. One was our adaptive supervised learning approach, and one was a baseline approach that only trains C-star style of classifiers for the intermediate concepts. So these are the three settings. In all the cases, the agent was able to align with the preference of the user. And we can see that when the number of intermediate concepts are the same, the total queries required by the adaptive learning approach is less than the baseline. Okay, so this is the current state of the work. And now I'm going to talk about the improvements I want to make, particularly to this preference specification component of our framework. Okay, so the first thing I want to try, the two things I want to try is basically, the first thing is we want to see if we can use some pre-trained vision language model to bootstrap learning of the concept classifier, because these have been shown to be really good in like zero-shot classification tasks. We want to see if we can fine-tune these VLMs for training concept classifiers instead of training a CNN from scratch, see how much advantage we get here. The second thing we want to do is incorporate active learning into our framework, which has a very similar objective of trying to learn classifiers with little feedback from the user. The issue and the reason why we did not use active learning initially was because these have been shown to fail in environments where there is an imbalance in the data set. But since we have circumvented that problem in our approach, what we can do is, once an initial concept classifier is learned, we can do a few rounds of active learning to quickly increase the accuracy of the class. So this is this is more of a technical improvement that we want to try. The second is more about the evaluation of this against the approaches that are more common in literature, which are the preference-based reinforcement learning approaches, abbreviated as PBRL, or now called reinforcement learning through human feedback, where the user is basically shown two trajectories, and the user is asked to rank, hey, which one adheres to your preference more, which one do you like better? So we want to see if between our approach and their approach, whether our approach has some reduction in the number of queries required to learn the preferred policy. And more importantly, we also want to do a human subject study where we want to compare the cognitive load between these kinds of queries and the kinds of queries we are looking at, which are basically mainly labeled queries. And we also want to just see if users have a preference over what kind of query they like. Okay, so based on this, here is my estimated timeline. I want to complete this work by January 2024, then do the writing by April 2024, and tentative defense date would be May 2024. Okay. So, yeah, so this brings us to the end of the talk, where to summarize, we basically dealt with the problem of personalization and AI agents which have an inscrutable task representation. We saw how symbolic interfaces can be used to generate symbolic explanations, how we can generate personalized explanations, and how we can let users add new vocabulary terms to this interface. Thank you. That's the end of the talk.
There are any questions from any of you, and of course the committee members too? Go to slide 18.
Yeah, 18.
Yeah, that's.
Or is it something?
This is, let me see.
Yeah.
You change it. Sorry, 19. So here, probability of concept C not a precondition of A. Probability of concept C state as. Yeah, can you explain the intuition a little more?
Yeah. So essentially what we are seeing here is, let's say that, okay, so the way this is working essentially is, let's say you sample a state, action A is executable there, and the concept C is present in this state, right? Now, what we are saying here is that, and we see all the concepts that are present in this status, right? And we want to know whether this concept C is a precondition of that state. Now, what this is saying is, if you see this concept C anyways with all the other concepts that are in status, like let's say that concept is very common, it is correlated to a lot of other concepts, right? So you end up seeing this concept a lot with all the given all the other concepts in the state. So that means intuitively that it could just be that it is correlated. It's not really a precondition of that action. So that is what is this formula is capturing, that if that is the case, the possibility that it is not a precondition is still high, and you would need to have a lot more samples before you are confident. Yeah.
And that's the only time I saw, or maybe I missed, is about this precondition, right?
Yeah.
So if this is kind of so if this is low, then it is a precondition.
So if this is low, then yes, it is a precondition, because 1 minus this is the probability that it is a precondition.
Yeah, I mean, so if some concept is present, just happens to be present, everything is a precondition.
Yeah, yeah. So that's what we are trying to sort of circumvent here. But that it is very commonly present, then we keep on sampling, like we'll keep on sampling a lot till we are sure that, okay, every time we can see that this action is executable, the concept is present.
Like, I would think the way you would be is that something is a precondition if when it is there, the action you can do. When it is not there, if you do the action, you are not able to do, or something like that.
Right, except like that is true, and if it is not there, then we can remove. Yeah, then we can remove it. If you have a good classifier and we see that the concept is not there, we can certainly remove it. And that is how our sampling procedure works initially. That is exactly how our sampling procedure works. That if a concept is not present in the state where the action was executed, we will remove that. But what we are saying here in this particular, once we consider confidence, is that actually the thing is, we're also considering the fact that there can be noise in concept classifier. So just because you are seeing it doesn't mean that it is definitely true. So that is kind of also being accounted for.
I also have a question about this. What is Z? What is prior? And how did you get this? Or this is like your
high level.
Your high level.
Yeah.
It's not you. It's not your derivation from something. It's just it's a representation of your heuristic or something.
Yeah, given this.
How do I know this is true?
So this we got, like, assuming this Bayes models, we can do computations to get to something like this. Yeah, it is a high level formula, but like I have the more detailed version in the proposal document. But yeah, this is what we have.
So you also have a definition of prior.
Prior is just the prior is just like what we start with, like the uniform prior, for it not being a precondition.
Yeah, I was looking for the beginning. So what is the starting point for concepts? I mean, if you have the simulator and all this, the images, right?
Yeah.
And so I was looking at the slide 11 when you start talking about vocabulary and concepts. So how do you get the left door close? Like, what is the starting point of this?
Right. So there are two ways we did it here. In one case, we defined it ourselves. Like, we are assuming that we have this somehow predefined. But the way we did it in that second domain was we actually conducted a survey where we let people play the game themselves, and we asked them, okay, can you tell us the kinds of concepts that you think are relevant to like action executability and the cost.
So through interaction with.
Yeah, they interacted, they gave us, like, this is a concept that seems to be relevant, this is our description, then we collected, grounded in our sense.
So yeah, I think your proposed work is going to be very important. I wonder actually if you give that image to which one GPT-4 and say what is out present in this or and what it finds.
Yeah.
So I guess with this modern latest LMMs or whatever, probably you can get some of those.
Exactly, that's the whole point. But the thing, what I at least believe is that is actually a stronger evidence to move against approaches that are non-symbolic. Because if, let's say, the concept classifiers are already very good with these visual language models, we can even move further away from approaches where we're just showing them two trajectories and asking them to compare. So even if that's the case, that's good. The other is that we would still hopefully like need such systems that can do grounding, because there could be like specialized domains which have like specialized concepts which are anyways not very common knowledge. So in those cases, these systems can still be somewhat useful.
And similarly, in like slide 28, where you're starting with the explanatory messages, could one use LLMs to have some?
Yes, definitely. Like, you will have to start with a good description of a domain, and then the LLM can basically sense what kind of things user would mostly find inexplicable, and then what kind of explanations would be required for them. So for common sense knowledge domains, possibly this can. Yeah.
So on this work, my question was, when you are giving explanations to the users, different users, do you assume that they all know that it's the same thing? They're aware of the fluence? Is it possible, because for the other works you have that people may not know of certain fluence and then you're trying to discover them?
Yeah, the assumption is that they understand the symbology. So like once we give them whatever the model parameter is, that is actually being updated in there. So that is a premise.
What is yes. You mentioned about explainable and advisable. I have seen your discussion about explainable. What is the advisable?
Right. So when I say yeah, so here when I was basically sorry. Yeah, here basically by advisable, I essentially means that there's a user and an agent, and the user wants to either give instructions to the agent, hey, do the task this way, or they want to specify some preference about do the task in the way that it aligns with my preference. So that is what we basically call under the umbrella of giving advice.
Well, I haven't seen your discussion about this. Oh, when you do reinforcement learning, that means PR working.
So the third component where we are letting user the third component of the talk was about letting users add new terms to the vocabulary. So there the underlying problem was that using this vocabulary, the user will want to specify some preference. So that is our version of letting users give advice or preference to the agent.
The user give.
Yes.
And also, you mentioned about the contrastive stuff and 12 or something, right?
Yeah.
Contrastive.
I believe that's what's the thing.
So how do you generate the contrastive?
Right. Yeah. So here we had contrastive theories like why do X and why not do Y. So in this case, like there are two ways to basically invalidate Y. That why did the agent do X and not Y? So this is coming from the user, and the agent is going to explain why it did the plan X and not Y. So there were like two ways we were doing it. One was either prove that the foil plan being suggested by the user has an invalid move. So that could be a move that is not executable in the state where the user wants the agent to take that action. So it's not possible to execute that action, or it is violating some hard safety constraint of the environment. So, for example, this is one of those foil that the user suggested. Instead of going over the skull, this is the original plan where the agent said, I'll go over the skull. And the user said, why don't you take the action move left, that is go through the skull. That's when the agent can say that move F will fail because the precondition skull not on left is missing. What this basically means is that this skull not being on left is required for agent to go on left. Otherwise, the agent will die, and that is like a safety constraint. Like that, as the game gets over. So that is why this action move left is an invalid move.
My question is, how do you generate these? Like you can have many, not Y. Usually, contrastive is not X, right? X, not X. You have not Y. So, do you see the formula? You said 11.
Yeah.
Right?
Yeah.
YX, not Y. But contrastive.
Right.
So you can have many, not Y. Why? So how do
It's
you?
just the why, not why that the user asked. The user is specifically asking, why did you do this decision as against other decision? So you just want to.
So in this case, like robot tries to correct the user.
Yes, the robot is. So the user has some knowledge missing about the domain, which is why he's getting confused. He's saying, why don't you just go through the skull or attack the skull?
So who has higher status?
Yeah, I mean the rather it has the more accurate model of the task than the user has.
And also you have a lot of explanation, types of explanations. You have like concept-based, salience and map-based, conformant and personalized explanation. So what are these explanations?
So, right. Concept-based explanation is basically, in general, so according to the classification I'm seeing here, personalized is type of concept-based explanation. But the two concept-based is basically whenever the agent is using some symbolic information, like some term from the user's vocabulary, and that is a concept. Like here the concept is that when the skull on left is true, this is the concept. In that case, the action cost is greater than 5. So this is a kind of concept, and this is a kind of concept-based explanation. Saliency map-based explanation would only like highlight. So if I were to use a saliency map explanation over here, most likely it will just highlight this part of the skull, and it wouldn't really be clear as to what it means and why exactly is this still more costly. So those are what I'm calling saliency map-based explanation. Then there is personalized explanation.
Yeah.
So personalized is basically where you are in this sense, at least in personalized is where we are saying that at a high level, each user is so different that personalized is more about, so in this particular example, let's say that the user has a different vocabulary altogether. So the user of type A thinks that this concept is called skull on left. User of type B doesn't even call this a skull. It calls it an enemy on left. So if I say skull on left, maybe they don't understand. So that's the kind of distinction we are making, that the users could have different vocabulary, or users could have different knowledge to begin with, and that could change the explanations we give to them.
So what is the example of conformant?
Oh yeah, so conformant explanation would in this case be like we'll have both the things, like skull on left and enemy on left. In both these cases, attack action costs greater than 500. Conformant is that if you have two types, so this would be a better example here. So here in this disaster rescue domain, we have two users of two types, right? Picking a first aid and user type B thinks that going over puddle can damage the robot. So we'll generate.
What are these type of explanation? It is a concept based or it's a salient? It's a concept.
It's a concept. It's a symbolic.
Yeah, but then you have conformant and personalized. How can I make it personalized?
So yeah, the whole point is that you have to first. So you don't, to begin with, you do not know what type of user you are interacting with.
But to me, it's just these are just a different explanation, not personalized, right? Are they personalized or they are just a different text?
I mean, they are as opposed to conformant explanation would be me giving both these explanations.
Oh.
Personalized is I'm only picking one of them. So I know you are of user type A and I'm going to just give you this. I won't reveal this because you already know this.
How do you know what a user believes?
Okay. So that is what we are learning from the data in the training stage. So we are detecting what types of users exist from the data. From like basically we collected a lot of interaction data from a lot of users.
Okay.
We make models of each of the users. What is their model? So we ultimately know that user of type A believes this, user of type B believes this. Then what we do during our interaction stages that will basically see if, okay, so this is a crude example, so it doesn't work exactly here, but let's say there was some common, okay, let's say that this is what the agent can do, right? Let's say it picks up this first aid kit, but doesn't give an explanation. The user will then say that, oh yeah, why didn't you pick up this? This seems to be an inexplicable action. I don't understand it. Instantly, you know, okay, this is of user type A, and all the further concepts, all the further things you give can be personalized to user type. So the labels we get from the user are the evidence of what their actual type is.
Okay, so you said E, right? Small letter E is explanation.
Yeah, those are
in the big letter E.
Yeah.
So you have it's all predefined. The big letter.
Yes,
E.
that we are assuming is like a domain expert or someone has given us what are the possible explanations that could be needed for the end user. Like these are all possible.
So in that E, big letter E, you also have these different types, like a concept-based and salience.
No, those are just symbolic explanations. Basically, they'll essentially these will each of the messages in E will correspond to some information about the underlying task. For example, it could be just saying that the reward for going into a state that has a puddle is essentially 0. So this is the kind of explanation we want to give to user type B, which believes that actually the reward for going here is negative. So we want to give that explanation to this user. Okay. So they know going on the puddle is fine.
In your formula, you also have L, right? L, label.
Exactly. Yeah. So label is
label is the which type of user?
Label is whether they would find a transition to be explicable or not, given some explanation. That's the label of the.
What is your most important task for this work? Just try to learn the classifier?
The most, I would say that it has like 2 parts. One is we want to see what are the user types that exist for the task.
That's how you try to infer
from it. So
in a reverse order, right?
So that happens when the actual user comes in and actually interacts with the agent. That is the part B of the system. Part A is to first detect what are possible types of users. So you haven't begun with the target user interaction. You're just in a training stage where you're just trying to see what are the kinds of users that can exist for the task. Once you have a sense of that, then the actual interaction with the actual user will begin, and that is sort of like test time, right? And then you have ways in which you can infer that user's type and personalize it.
So, in essence, your work is try to let robot help the user intelligently, or
Basically, we don't want to overwhelm them with a lot of information. We want to
you
make
don't want to
sure
overwhelm users.
we do not want to overwhelm users with a lot of information. So imagine a system. This is like we are saying that it is much better if the user of type A is interacting with the robot, then we only give this explanation. We do not give this explanation, which we do not give this additional model information about the domain because that would be unnecessary, like extraneous information for
So that's why you want to first you want to infer
their type.
user type.
Yeah, exactly.
Then you try to provide
Yeah,
explanation
based on
based on it
yeah, that's
So-
the
through learning a classifier. So what's the
Yes.
classifier here?
yeah.
The
So-
use of classifier.
Yeah, so the use of classifier is something we have. The classifier is essentially a labeling model. So this is the classifier.
Yeah.
These are the inputs. These are the outputs. The classifier is essentially gonna say, given this transition,
Yeah.
SAS dash. So here it would be in this particular example. Here it would be this is the S. Action is to move right. S dash is where there is a puddle in this state.
Mhm.
Right? So this is puddle is here in the state.
Yeah.
There is no explanation, and then it would map to 0 because the user of type B will find this transition to be inexplicable. But if E is this message that reward for going into the puddle is actually 0, then the user will find this to be explicable. Okay, I understand why you did that.
Okay.
So we
So-
basically approximate the user's model in this form.
This zero means that this zero says E is not explainable. One means E is explainable.
Yeah, 0 means that given this explanation,
Uh-huh.
this transition makes sense to the user. It is
Okay.
explicable. Given the set of that's
Okay.
Any other public questions? If not, then you guys can leave. And you should stop the recording.
yes.